A database sails through a 15-minute load test, fast and responsive, so it ships. 2 hours into real production traffic, it slows to a crawl, the kind of speed you'd expect from a spinning disk back in 2005. Nothing changed in the code. The storage volume simply ran out of something the test was too short to exhaust. This is Cloud Architect Path from Stack Lessons. On with it. By the end of this video, you'll be able to pick the right storage for any EC2 workload, block, file, or ephemeral, and choose the exact EBS volume type from the numbers in the scenario. This sits in the high-performing architectures domain of the Amazon Web Services Certified Solutions Architect Associate exam, and the answer usually turns on one qualifier. Over the last few episodes, we built compute that scales itself, and databases that survive an availability zone going dark. But every one of those instances needs storage attached to it. And here's the thing. Pick the wrong storage primitive, and you quietly undo all that careful design. So this episode is about matching the right storage to the right compute, block, file, and ephemeral. Before we go deeper, 5 terms anchor everything else in this video. Amazon EBS is block storage that attaches to one EC2 instance in a single availability zone. The operating system treats it like a directly attached disk. Amazon EFS is a managed file system that thousands of Linux clients can mount simultaneously, spanning multiple availability zones. Instance store is local disk built into the physical host, the fastest option you can get, but every byte disappears the moment that instance stops. GP3 and IO2 block express are the 2 SSD volume types that cover most real workloads. GP3 is the sensible everyday default, IO2 block express when you need mission-critical performance guarantees. Finally, EBS multi-attach lets a single IO2 volume connect to up to 16 instances in the same zone, which matters for clustered database setups. Before any volume types, you need the bigger picture. Amazon Web Services gives you 3 fundamentally different ways to store data. Block storage, which is EBS, is a raw disk that the operating system formats and manages, and it attaches to one instance. File storage, which is EFS, is a shared directory that many instances mount at the same time. And object storage, which is S3, is data you retrieve by its key over an HTTP interface. You never mount it like a disk. Each one solves a different problem, and reaching for the wrong primitive is the classic misstep the exam loves to set up. Here's a mental model that makes the difference stick. EBS is a raw hard drive plugged into one computer. The operating system manages every sector, and it belongs to that one instance. EFS is a corporate network file share. Multiple employees open the same shared cabinet, and everyone sees the same folder hierarchy. And S3 is valet parking. You hand over your car and get a numbered ticket. You can't wander the lot or change a tire in place, but you can retrieve or replace the whole car instantly with that ticket. That last point is why S3 can never replace a file system. There's no editing a file in place, only swapping the whole object. You can turn all of that into a decision tree, and this handles most storage questions before you even read the answer choices. Start at the top. Does the data need to survive the instance stopping? If not, and you just need raw speed for a cache or scratch space, instance store is your answer. If yes, ask the next question. Is it shared by many instances at once? If it is, and those instances are Linux, that's EFS across multiple zones. If only one instance needs it, that's EBS, with GP3 as your default. And if you don't need a mounted file system at all, just API access to objects, you're looking at S3 instead. Let's go deep on EBS, because it's where most EC2 workloads land. An EBS volume is a network-attached disk, and it's locked to a single instance in a single availability zone. But here's the important part. It persists independently of the instance. You can stop the instance, and the volume and its data are still there. That single AZ scope, though, is something to keep in mind. It shapes how you protect that data, which we'll come back to. EBS gives you 6 volume types, and they split into 2 families. The SSD family, GP3, GP2, IO2 block express, and IO1, is built for IOPS and random access, the kind of work a database does. The HDD family, State1 and SC1, is built for throughput and sequential access, streaming large files start to finish. One quick rule that saves you time: SSD types can be boot volumes, HD types cannot. We'll take these one at a time because the exam anchors on specific numbers for each. Start with GP3 because it's the modern default and a recurring right answer. Every GP3 volume gives you a guaranteed baseline of 3,000 IOPS and 125 MB per second of throughput. And that baseline is the same whether the volume is tiny or enormous. It costs about 20% less than the older GP2. And critically, it never uses burst credits. It just delivers its performance all the time. When a question asks for the most cost-effective general-purpose volume, GP3 is almost always the answer. The headline feature of GP3 is that it decouples performance from size. Picture the difference as 2 hotels. With GP2, your room service speed depends entirely on which floor you booked. Higher floors get faster service. Its performance is 3 IOPS per gigabyte, so to get more IOPS you have to buy a bigger volume. If you want 10,000 IOPS, you're forced to provision over 3,000 gigabytes of storage you don't actually need. GP3 is the hotel where you pick your room size and your service speed separately. You get 3,000 IOPS baseline on a 20 gigabyte volume or a 20 terabyte volume, and you can scale up to 80,000 IOPS and 2,000 megabytes per second for a fee on any size you like. So why does GP2 collapse the way our opening database did? It's the burst credit mechanism. Take a 100 gigabyte GP2 volume. At 3 IOPS per gigabyte, its true baseline is just 300 IOPS. But it starts life with 5.4 million IO credits, and those let it burst all the way up to 3,000 IOPS. Under sustained heavy demand, that credit pool drains in about 30 minutes. When it runs dry, the volume falls back to its baseline, 300 IOPS. That's roughly the performance of a spinning disk from 2005. A short load test never lasts long enough to empty the pool, which is exactly why the problem only shows up in production. Think of the GP2 volume as a phone with a slow charger. Fresh out of the box, the battery is full, and the phone feels snappy. But under heavy sustained use, the battery drains faster than the charger can refill it. Once it's empty, the phone drops into low power mode. That's your baseline IOPS. And the smaller the volume, the slower the charger. GP3 has no battery at all. It's just plugged straight into a constant power outlet at 3,000 IOPS forever. Here's the same story in numbers for that 100 gigabyte volume under sustained load. In the first 30-something minutes, GP2 bursts along at 3,000 IOPS. Looks great. Once the credits are gone, it drops to 300 IOPS, a tenth of what you were seeing. GP3, meanwhile, holds a steady 3,000 IOPS indefinitely. Same workload, no cliff. That gap is the whole reason Amazon Web Services pushes GP3 as the default now. Amazon Web Services states it plainly in the EBS documentation. GP3 volumes do not use burst performance. They can indefinitely sustain their full provisioned IOPS and throughput. That single sentence is the distinction the exam tests between GP2 and GP3. No credits, no cliff, no surprise slowdown 2 hours into production. Now, how do you actually move off GP2? This is the part people love. Using a feature called elastic volumes, you change the volume type while it's running. No stopping the instance, no detaching anything. Every volume you migrate gains that guaranteed 3000 IOPS baseline regardless of size, and your EBS bill drops around 20% at the same moment. So when a question asks how to improve storage performance with minimum downtime, migrating GP2 to GP3 with elastic volumes is the move. When GP3 isn't enough, you step up to IO2 Block Express, the top tier. If GP3 is a fast consumer SSD in a laptop, IO2 Block Express is an enterprise NVMe array inside a financial exchange. It delivers up to 256,000 IOPS per volume, average latency under 500 microseconds, and 5 nines of durability. That's 99.999%. This is the answer for mission-critical databases like SAP HANA, Oracle, and SQL Server, where sub-millisecond latency is a hard requirement. The documentation gives you the exact figure. IO2 Block Express is designed to deliver average latency under 500 microseconds for 16 kilobyte operations, and it cuts the frequency of operations exceeding 800 microseconds by more than 10 times. So it's not just the average that's fast. The worst-case tail latency is compressed too. That matters enormously for financial transactions and real-time analytics. When you see sub-millisecond latency or IOPS in the hundreds of thousands, this is your answer. You may also see IO1, the previous generation of provisioned IOPS. Here's the comparison. IO1 tops out at 64,000 IOPS and has a durability of around 99.8 to 99.9%, and it caps you at a 50-to-1 ratio of IOP per gigabyte. IO2 Block Express reaches 256,000 IOPS, offers 5 nines of durability, 100 times higher, and allows 1,000 IOPS per gigabyte, far more flexible. And the two cost the same. So for any new provisioned IOPS workload, IO2 beats IO1 on every single dimension. If both appear as options, IO2 is correct. That covers the SSD family. Now the HDD family, for when throughput matters more than IOPS. ST1 is throughput optimized, reaching up to 500 megabytes per second, perfect for Kafka log streaming, big data, log processing, and ETL, where you read and write large files sequentially. SE1 is cold HDD, the cheapest block storage on Amazon Web Services at about 1.5 cents per gigabyte, made for archives you rarely touch. Both are cheap per terabyte, but capped at just a few hundred IOPS, so they're terrible for random access. And remember, neither can be a boot volume. The moment a question mentions a root or boot disk, you can eliminate both immediately. Here's the whole EBS lineup on one screen. GP3 is your default, with a 3000 IOPS baseline and a maximum volume size of 64 terabytes. GP2 is the legacy version with its burst credits. Migrate off it. IO2 Block Express is the top tier at 256,000 IOPS and sub 500 microsecond latency for SAP HANA and Oracle. IO1 is the older provisioned IOPS option. ST1 is throughput optimized HDD for Kafka and big data, and C1 is the cheapest for cold archive data, and neither HDD type boots. If you memorize just one row, make it GP3. 3000 IOPS and 125 megabytes per second baseline, scaling to 80,000 IOPS and 2000 megabytes per second at maximum. Let's lock in the block layer before we move on. EBS is single instance, single AZ block storage. GP3 is the modern default, and GP2's burst cliff is exactly why. When you need sub-millisecond latency or IOPS in the hundreds of thousands, you reach for IO2 Block Express. And for cheap sequential throughput, ST1 and SE1 do the job, but never as boot volumes. Now let's leave block storage behind and look at what happens when many instances need to share the same files. EBS attaches to exactly one instance. But what if a whole fleet of servers needs the same files at the same time? That's where EFS comes in. EFS is managed NFS, a network file system that thousands of Linux clients across multiple availability zones can mount concurrently. And it's elastic. It grows and shrinks to petabytes automatically with no capacity to provision. You just mount it and it's there for every instance. Picture EFS as a shared drive for your fleet. It's like a Google Drive folder that every Linux server mounts as a real directory. When one instance changes a file, all the others see it instantly. No synchronization scripts, no copying content around. Think of a media company running a content management system across an autoscaling group. Every new instance mounts EFS at launch and immediately sees all the existing uploads. Capacity grows and shrinks on its own, so you never provision a size. The one trade-off is that it's a network folder, so raw random access latency runs a little higher than a local EBS disk. Amazon Web Services spells out the core differentiator. EC2 and other compute instances running in multiple availability zones within the same region can all access the file system, so many users share a common data source. That's the line to remember. Multiple instances, multiple zones, one shared source. That's precisely what EBS cannot do, and it's the cue that a question is pointing at EFS. Here's a distinction that quietly decides questions. EFS speaks NFS with POSIX permissions, which means Linux only. No Windows, no SMB protocol. Amazon Web Services states directly that using EFS with Windows-based EC2 instances is not supported. So if a scenario mentions Windows or Active Directory alongside a shared file system, the answer is FSX for Windows File Server, not EFS. We'll cover FSX on its own in the next video. Let's put EFS and EBS side by side. EFS serves thousands of clients across multiple zones at once, grows to petabytes automatically, and costs around 30 cents per gigabyte, but that one file system serves the whole fleet. It's Linux and NFS only. EBS, by contrast, is one instance in one zone. A fixed size you provision and grow by hand at around 8 cents per gigabyte for GP3, but that's per instance. EBS runs on any operating system and gives you database-grade low latency. Different tools for different jobs. Shared access versus dedicated speed. Now, on paper, EFS looks more expensive, 30 cents per gigabyte against GP3's 8. But that comparison misleads you, and the exam knows it. Say 50 instances all need the same shared content. One EFS file system serves all 50 without duplicating a single byte. To do the same with EBS, you'd need 50 separate volumes, each holding its own copy of that same content, 50 times the storage. So when a question asks for the most cost-effective shared Linux file system across multiple availability zones, EFS wins, higher per gigabyte price and all. There's one more sharing option that people confuse with EFS, and that's IO2 multi-attach. Multi-attach lets a single block volume connect to up to 16 instances, but only within the same availability zone, and only if you're running a cluster-aware application like a SQL Server failover cluster or Oracle RAC that coordinates writes. It's a clustering primitive, not a general file share. EFS is the opposite. One file system, thousands of clients across multiple zones with general shared file access and no clustering coordination needed. So if a question mentions multi-AZ shared access without any clustering, that's EFS. Same AZ clustered database, that's IO2 multi-attach. That leaves one more storage option, and it's the fastest of them all, Instance Store. This is local NVMe storage physically attached to the host machine your instance runs on. It delivers the highest IOPS and lowest latency of anything on EC2, faster even than IO2 Block Express. But there's a catch that defines everything about it. The moment the instance stops, that data is gone permanently. Think of Instance Store as a whiteboard right next to your desk. It's blazing fast to write on and read from, latency of 20 to 100 microseconds. It survives a reboot, the way notes stay on the board overnight. But leave the building, stop the instance, or if the building burns down, meaning the host hardware fails, everything on that whiteboard is gone. There's no additional charge. It's baked into the instance price. Instance Store isn't limited to storage-optimized families. You'll also find it on certain generations of compute-optimized and memory-optimized instances. Within the storage-optimized lineup, the i4i uses Intel NVMe SSDs, while the i4G, M4GN, and ICE4 Gen families use Amazon Web Services designed Nitro SSDs for raw local throughput. Instance Store beats even IO2 Block Express. Amazon Web Services is precise about what Instance Store is for. It's ideal for temporary storage of information that changes frequently, buffers, caches, scratch data. Notice what's not on that list? Anything durable. A machine learning team writing multi-gigabyte training checkpoints to local NVMe is the perfect use, blazing fast, and the scratch data is meant to be thrown away. When training finishes, the final model gets copied to S3 for safekeeping. The engineering rule here is simple. Instance Store is ephemeral by design. The moment the host stops, restarts, or fails, everything on it is gone. So if a requirement mentions data that must survive a stop, a restart, or a host failure, words like durable, persistent, or must not be lost, Instance Store is off the table. It belongs on caches, buffers, scratch space, and data you can cheaply regenerate. Anything else needs EBS, EFS, or object storage. Here's the trade-off at the heart of it all. Instance Store gives you peak speed, the fastest local performance on EC2. But it has no durability guarantee at all, because the data doesn't survive a stop. IO2 Block Express offers 5 nines of durability, 99.999% for your mission-critical data. And GP3 sits at around 99.8%. The lesson is simple. You're always choosing between raw speed and data survival, and the right pick depends entirely on whether the scenario says the data can be lost. One last thing on EBS that shows up in resilience questions. EBS does replicate your data, but only within its single availability zone. That's hardware fault tolerance, not zone protection. If the whole availability zone fails, that volume is simply unavailable. So how do you escape the single AZ boundary? Snapshots. EBS snapshots are incremental backups stored in S3, which is regional and spans multiple zones. From a snapshot, you can restore a volume into any zone in the region, or copy it to another region entirely for disaster recovery. EBS replication does not protect against AZ failure. Snapshots do. Let's tie it all together with the decision rules. For single instance persistent block storage, reach for EBS GP3. That's your default. For sub-millisecond latency, or hundreds of thousands of IOPS, IO2 Block Express. For a shared Linux file system across availability zones, EFS, and never for Windows. For the highest IOPS with no durability requirement, Instance Store, strictly for caches and scratch. And 2 rules that eliminate wrong answers fast. No HDD volume can ever boot, and EBS lives in one zone, so only snapshots escape it. Now let's see how well all of that stuck with a quick 5-question quiz. Let's test what you've learned. Question 1. A team deploys a database on a 100 gigabyte GP2 volume. It runs well during a 15-minute load test, but slows dramatically about 40 minutes into sustained production traffic. What's the most likely cause and the best fix? Is it A, the instance is undersized, so move to a larger type? B, the GP2 volume exhausted its burst credits, so migrate to GP3 using elastic volumes? C, the volume ran out of storage capacity, so expand it. Or D, network throughput to EBS is saturated, so add a second interface. Pause here if you want more time. This one is B. That 100 gigabyte GP2 volume has a baseline of just 300 IOPS, and it bursts to 3,000 using credits that drain in about 30 minutes of sustained load. Once they're gone, it drops to baseline. Exactly the pattern here. Migrating to GP3 with elastic volumes gives a constant 3,000 IOPS with no credits and no downtime. Question 2. A fleet of Linux EC2 instances in an auto-scaling group spanning 3 availability zones must all read and write the same uploaded media files, and new instances need to see existing content immediately. Which service fits? A, an EBS GP3 volume attached to each instance. B, an IO2 block express volume with multi-attach. C, instance store on each instance synced by a script. Or D, Amazon EFS mounted across all instances. Think about which one crosses zones and shares by default. The right call here is D. EFS is managed NFS that thousands of Linux clients across multiple zones mount at once. So every instance shares the same files and new ones see existing content the moment they mount. EBS is single instance. EO2 multi-attach is locked to one availability zone, and syncing instance store by hand is fragile and ephemeral. Question 3. A mission-critical SAP HANA database needs over 200,000 IOPS per volume and consistent sub-millisecond latency. Which EBS volume type delivers? A, EO2 block express on a Nitro-based instance. B, EO1 provisioned IOPS SSD. C, GP3 with maximum provisioned IOPS. Or D, ST1 throughput optimized HDD. Lock in your answer before I give it away. It has to be A, and here's why. IO2 block express reaches up to 256,000 IOPS with average latency under 500 microseconds, the only type that clears these numbers. GP3 tops out at 80,000 IOPS and IO1 at 64,000, so both fall short. And State 1 is an HD built for throughput, not IOPS. Note it needs a Nitro-based instance to hit that peak. Question 4. A distributed training job writes large temporary checkpoints between epochs and needs the absolute lowest write latency. The checkpoints are regenerated each run and don't need to survive an instant stop. What's the best storage? A, an IO2 block express volume for durability. B, Amazon EFS shared across the cluster. C, instant store, local NVMe on a storage optimized instance. Or D, an SE1 cold HDD to minimize cost. Got your pick? Let's see. If you said C, well done. Instant Store gives the highest IOPS and lowest latency on EC2, and the scenario explicitly says the data is temporary and regenerable, the exact use case for it. Durability isn't required, so IO2's persistence buys you nothing here and is actually slower for raw local writes. The word ephemeral in the requirement is your green light. Last one. A company runs a shared file system used by hundreds of Linux-based EC2 instances across 3 availability zones. A new project requires adding Windows Server instances that also need access to the same files. Which solution supports both the existing Linux workloads and the new Windows workloads? A, keep EFS and mount it to both Linux and Windows instances using NFS. B, replace EFS with an IO2 multi-attach volume shared across all instances. C, use EFS for Linux instances and a separate EFS file system for Windows instances. Or D, migrate to Amazon FSX for Windows File Server and access it from both Linux and Windows using SMB. Run the decision rule from earlier before you answer. The answer is D. EFS speaks NFS with POSIX permissions, and Amazon Web Services explicitly does not support mounting EFS on Windows instances. So options A and C are out. AO2 multi-attach is a block-level clustering primitive limited to a single availability zone, not a general file share, so B is wrong too. FSX for Windows File Server uses SMB, which Windows instances speak natively, and Linux instances can connect via Samba clients. Okay, high-performing storage, EBS, EFS, and Instant Store, done. If you're getting value, subscribing is the best support there is, and it spreads these wider. Let me know in the comments what helped and what didn't. Want a different cert covered? Suggest it below. Those requests really do decide what's next. And tell me how the pacing and visuals land for you. See you in the next lesson.